Hey, good afternoon, everyone. My name is Rez Mani, and I work for the company Allied Scientific Pro. The title of today's webinar is NIRvascan, a spectro-Photometer, and the newly introduced cloud service. I've given this webinar a number of times, and we try to modify the webinar every time to reflect the new activities of the company. And in fact, we do have some new results that I'll show in this webinar. The webinar is being recorded, and the recording will be sent to you within a few days. We'll also have a Q&A session at the end. My email is also mentioned here. If you have any questions, you can send me an email. So we have a long list today to look at, and we try to do as much as possible. We'll look at the difference between the NIR and mid-IR spectroscopy, and what is the advantages of NIR and need for a portable NIR spectrometer in various applications. Then we'll look into the digital light processing technique and compare it with the linear array detector spectrometers. And then we'll introduce different models of NIRvascan, their spectral range and their function, how to record a reference, and then we would get into the very important topic of chemometrics, of how to analyze the data, the NIR data, to extract information quantitatively and qualitatively. We have some examples: sweetness of fruits, protein and moisture content of wheat kernels. And then I would like to demo the cloud service, which we have developed, called NIRvacloud, for nearly about 15 minutes. And then we would just go into looking at the deep scan demo app and some case studies for each of the units: the reflective unit, transmission unit, and the fiber optic unit. We have a few case studies that we will discuss, and then look at a few proposals: flow measurement proposal, the ISC NIRvascan app. I'll discuss that a little bit. And finally, the NIRvascan in scientific literature. So this will be our agenda here today. Okay, so let me move on. I can also activate the laser pointer here, so that will be better. So here we see on the right side the electromagnetic spectrum that is going all the way from the gamma ray all the way to long radio waves. And the near IR region is right here, right next to the far red. So from 780 to 2500 nanometer, we call it near IR. From 700 to 780 is called far red, and that's part of the that's part of the IR spectrum. So 400 to 700 nanometer is the visible, and 700 to 780 far red, and 780 to 2500 is near infrared. So this was discovered by William Herschel in 1800, where when he put a thermometer right next to the red spectrum where there was no light, and he saw that the temperature increased. So he deduced that there should be a radiation there that causes this increase. And later on, he verified that this radiation indeed exists because it's a wave that follows the laws of reflection, refraction, and interference. So look, if we look at the different regions, we have 780 to 2500 nanometer, as I said, is near IR, then mid IR 2.5 to 25, and then far IR is 25 micron to 1 millimeter. So when we think about the interaction of light with matter, we should consider the absorption of different frequencies corresponding to molecular vibrations, such as stretching, bending, wagging, and twisting. And you can see some of these modes here in these figures that we have here. Then, so molecules will vibrate and they will absorb corresponding frequencies that resonates with that vibration. So these vibrations, they have their frequency lying in the mid-infrared region. So those are the fundamental frequencies, for example, for CO, CH, CN, and NH bonds. So mid-IR bands are all fundamental frequencies. They're very strong and they're very distinct and narrow. However, the problem with the mid-IR instruments is that when the sample has too much water, the water absorption is so strong that it will swamp all the other signals. And you also need to do sample preparation and expensive, there's also expensive equipment. So another way of dealing with measurement of ingredients would be to use the NIRIR. And NIRIR uses the overtones, which are the multiple frequencies. You can see here the fundamental, then first overtone, second overtone, third overtone. And you can see that the intensity decreases with the increase in number of overtones. And you can also have a combination band, for example, combination of symmetric stretching and say rocking or bending. So these are combination bands. So although these spectra are harder to analyze and they're weaker in intensity, but still, because the action is quite fast, it doesn't require sample preparation, and you can also measure watery materials. It will be useful to measure it using NIRIR. So just to basically, just to show that the difference between the two set of spectra, you can see the mid-IR spectra here, the P and R bands for each molecules, N2O, CO2, and other molecules. They're very intense and they're very distinct. And as a comparison here is the NIR-IR spectra, which is a mixture of maybe overtones or combination bands and overtones, and they're not as intense and it's complicated. They're wide bands and they're overlapped, so you need to analyze this to get useful information out of it. So for this reason, we will introduce the chemometrics, which is a method of analyzing the NIR-IR spectra, because the information that you get is not straightforward. Okay, next. Oh, sorry. Yes. So the chart shows the absorption bands different molecules in the basically combination of far red from 700 to 780 and from near infrared from 780 to 2500 nanometers. And you can see that there are several regions. There is a combination band region here, first overtone, second overtone, and third overtone region. So our NIRvascan instrument actually works in the, or the standard model works in the 900 to 1700, and that is the second overtone region. We also have an extended NIRvascan that works from 1350 to 2150, and that's in the first overtone region. Okay, so these are the bands that help us to identify different ingredients. You can see H2O band, the CH band for fat and sugars. Also, you have the NH bands for protein, which you can use. Sorry, just gonna. Yeah, so now we're going to discuss the digital light processing or DLP method versus a linear detector. So what is the difference between the NIRvascan and a typical array detector? So in an array detector, in the array spectro-Photometer, you can say there are internal lights that shine to the sample. they get collimated and then hit the diffraction grating, and then they are basically dispersed into different wavelengths, and each element, each wavelength falls on a different pixel on the detector array. So this is how you can generate the spectrum. However, in the DLP method, the digital light processing that was introduced by Texas Instrument a few years ago or decades ago, the method is different. The initial part is the same, but instead of having a detector array, you have this micromirror array. So this has many small mirrors, and instead of using a detector array, we use a small single point detector. So what happens is that each mirror turns towards this detector one by one. So it turns, and then so the blue light goes there, and then it turns back. Then the green one turns, and the green light goes there, and it turns back. So one by one, they turn towards and away from the detector, and this way the spectrum is produced. So this has several advantages over the traditional detector spectrometer. First advantage is that the DLP micromirror array is less expensive than the detector array. So that would reduce the cost of the instrument. So for example, our reflective model is $2,000, which is less expensive than a typical photodetector that you may buy from another company in the US and or anywhere else. And there are also other advantages. One is the higher performance due to your use of larger single element detector, because you can increase the size of the detector, and that would increase the signal to noise ratio. You're not limited by the size of pixels in a detector array. And then also you can do custom patterns, because if you don't want, for example, to scan the full range, you don't have to. You can choose a section in there, let's say from 1,000 to 1,500 is only your region of interest. You can do a scan configuration that will only scan those. Or you can also do multiple pixels, different patterns. So if you want to increase the signal to noise ratio, you could use that. And I'll talk about the Hadamard scan configuration later. That will make it more clear. So these are some of the advantages of using the DLP method. This is the scheme or diagram of the instrument, and you can see two lamps at 45 degree and 145, and there's a sapphire window, and the scattered light goes in and then hits the mirror, and this is the DMD board, and this is the detector. So it also has a slit, which is 25 micron by 1.8 millimeter tall. So these are all the features, and they're all mounted on a circuit board. Next, we talk about the different models that we have here. So I'm sure you have looked at our website. So we have the reflection model or reflective model shown here. You need to put this window on the object, a powder, grain, or solid surface, and press the scan button. It will just detect the reflective, basically the diffuse reflectance from the surface. Then you also have the transmission model, which has a cuvette. You can pour a liquid in there. This is for liquids. So the measurement is done through absorbance through this cuvette. And we also offer the fiber model, which doesn't have an internal source, but as well as show you later, this could be used with an external source that can be triggered by the spectrometer. And this is one of the new things that I am showing in this webinar, which was not shown before. The range is 900 to 1700. The resolution is moderate, about 10 nanometers. And the detector is InGas, basically 1 millimeter InGas. So its performance drops off at around 900, and also at 1700. There are some temperature dependence issues. So the data that one can get in the 1650 to 1700 or 900 to 950, usually better not to focus too much on those regions because the detector has some extreme issues at those wavelengths. So detector has some, not extreme issues, but has some issues at those extreme wavelengths. That's what I mean to say. So better to focus in the range 950 to 1650 so that the detector already has a good response and is not temperature dependent. Okay, now we also offer the extended models. As you can see, there is the R11, the reflective model, and here this comes with a cooler. It needs to be cooled, and obviously it's a different detector. It's an in-gas detector, but it's an extended in-gas detector. Uncooled detector, it says, but one of the R11 needs an external cooler. You also have the transmission model, and you also have the fiber model. 1350 to 2150, which would basically looks at the first overtone region. If you remember, I showed you here. So this will be the first overtone region that these spectrometers will look at. So these spectrometers are more expensive, nearly about $5,000. So they are used mostly for special applications. For example, if you want to measure fat or glucose, sugar, you can easily do that with the standard NIRvascan. But for example, if you want to do cannabis, there is a THC band at 1950 that the standard cannot measure. So you need to use one of the extended models for that. Let's look at the software. This is the PC software that you will get for free when you purchase the instrument. We'll send you a link. You can download it. So this is how the main window looks like. And in the main window, you can see there's these three functions here: built-in, previous, and new. So what are these? So the reference signal has already been recorded in the factory, as in is in the instrument. So when you choose the built-in, this button turns into scan directly. So that means that you just can go ahead and scan directly. For any absorbance measurement, you need the reference. So you need the intensity and then the reference. So that's I over I0. So this I0 already been recorded there. So you can just go ahead and measure if you put it on built-in. But if you want to measure your own reference, then you need to put this on new, and then it asks you scan reference. You scan the reference, and then it will go to previous. So that means that this will turn again into scan. So this scan would use this measurement that you just did with the spectral launch surface. I'll show you this surface later. So you use your own reference. So the question arises, why would you want to use a new reference if you already have the reference recorded in the spectrometer? The answer to that question is that because this reference has been recorded with certain parameters. So their parameters is, let's say, averaging time, the exposure time, the pattern, and all the other parameters. I'll show you later. So if you're exactly using the same parameters, there's no need to record a new reference. But if you want to change some of these parameters, for example, you want to use the length, the scan width, or the gain, or something like that, you're changing a number of averages, for example, then you need to also record your reference with these new parameters. So it's not correct to use a reference which has different parameters from your current scan. And that's why you need to record a new reference. So obviously you have to connect your instrument with a cable to the computer, and then you can fire the PC software. Here are three graphs that you can get out of this. The reflected intensity, this is the reflectance function, which is I over I0, and then the absorbance, which is log of 1 over R. So normally for all the modeling, we always use the absorbance. That's what we are interested in. And you get an Excel compatible CSV file that you can use for your modeling. Okay, next is, so how do we calculate, how does the PC software calculate reflectance and absorbance? It's very straightforward, measures the intensity. It already has a reference, so divides I by I0, and then A is log of 1 over R. And for the transmission model is just replaces the reflectance by transmittance, so A is log of 1 over T. Pretty straightforward. And this is the spectral lawn surface that I was talking about if you want to record your own reference. So it has 97% diffuse reflectivity, 50 millimeter diameter, and you can purchase it from a company, StellarNet, nearly for probably about $300, maybe more, around anywhere from $300 to $500, model RS50. So here, as you can see, you put it in new, scan reference, and then the previous would use that reference. As long as you are doing the measurements, it uses your last measured reference. So the previous refers to the last measured reference. So you will use that. Next. Okay, how do we change the scan parameters and record the newest configuration? So if you look at the scan config tab of the software, you see there are already some existing scan configurations. So column 1, Hadamard, nitrate already there. And these are all the parameters, the range, the width, 7.03 nanometer, exposure time, and so on. So you can create your own scan configuration for whatever parameters you want to put. So you can create that and name it, and then you would basically, after you create your own scan configuration, you can run it every time. So you don't have to, if you know that, for example, you need 50 scans to average every time. You don't want to use the 6. So you create your own scan, and based on your custom scan, you can always run that scan. This is the app. You can also use an app that would communicate with the device via Bluetooth. And if you want to change your parameters, you could go to Quick Set. Normally you're on normal, but you can go to Quick Set, and then you can change the number of average scans, and also you can change this is the average times or exposure time. You can also change the exposure time if you want. I would not change any of the spatial wavelength related parameters, because you can say the app does not accept new references. It cannot record new references. So if you are changing only time related parameters like average scan or exposure time, it's okay to use the old reference which is in the instrument. But if you are changing any of the wavelength related parameters, then that measurement will not be correct. So if you are going to quick set, you want to change the number of averages from 6 to 10, you can just go ahead and do it. It uses the old reference. But if you want to change many of different parameters, including the spatial ones, I would not use the app. I would use the PC software and record a new reference with those new parameters. So I hope that part is clear. So here is the difference between column and Hadamard scan configuration that we talked about. So it's a matrix. These micromirror arrays a matrix. So I think I mentioned what the dimensions of that matrix is. 854 pixels. I guess somewhere it was mentioned 854 by 400 and something. 400 and I don't find it right now, but it's a matrix. So you can, in the column mode, you would only activate one column. So you could see this column, you can say that these are the 3 wavelengths that are activated. So, or you can also say that each column has only one of them. One of the mirrors are turning towards the detector. But in case of Hadamard configuration, you have multiple of those are turning towards the detector. So the first and the third, second and the third, you can see in the third, there are 2 of the mirrors are turning towards the detector. So this way you can do more multiplexing, and this would increase your signal to noise ratio. So the Hadamard would collect more light, basically, because more of the mirrors are turning towards the detector. And this way you can do multiplexing and you can increase the signal to noise ratio if you have any issues with signal to noise ratio. But in case of column, you only have in each column you have one of the wavelengths. So one of the mirror is turning towards the detector. You can do overlay plots in the PC software to compare different spectra. And here's an example. This feature doesn't exist in the app, so you can also use the software development kit that we provide if you want to modify the software to add more features that fits your application. We have it for both the app and the PC software. And now we look at chemometrics. As I said, we do need to analyze the NIR data because that's not straightforward. And for this reason, we use chemometrics. And some of the basic methods that we use are principal component analysis, PCA for sorting, also linear discriminant analysis for sorting. I'll show you some examples in the cloud. So when you want to, for example, sort different types of plastic, you need to measure the spectra, and then basically you get these different piles. When you do the score plot, this is the second component. This is the first component. It's called the score plot. So you could separate different materials from each other. Or you can also do the quantitative evaluation by creating a partial least square method or model. And here you can see predicted versus the average. So you need to make a calibration model for this. So you need to get a hold of 60 to 100 samples of varying amount of ingredients. So whatever you want to measure, sugar, moisture, or protein, you need to provide these samples yourself and get them measured by an analytical method in a lab. And then once you have these, then you would measure the spectra and make a calibration model. And then once you have this model, you would test its accuracy. And if the accuracy is good, you can apply that model to predict new samples with unknown ingredients, unknown amount of ingredients. So there are some standard softwares like Minitab that could do this kind of statistical modeling for you. Here I have done it for grapes, and you'll get an R square value, and there's also the parameter RMSE, root mean square error, that will tell you how accurate your model is. Here's also a webinar by Dr. Heather Brooks from Chem Analytics. We'll send you these YouTube links when we send you the recording of the video. So this is how you set up your spreadsheet. They have a standard software that they use called Unscrambler. But you can also do it in Excel and then use our cloud service, which we can introduce later. So all the horizontal lines are the spectra. So all the absorbances for each spectra are in the horizontal line. So this is the first spectrum, the second spectrum, third, and so on. And then the corresponding, in this case, protein content is in column 1. So you need to arrange your Excel sheet like that. And I will demo that when I demo the cloud service. And then you would run the make a model out of this and use as a calibration model. So as some examples, we did some modeling on grapes. So one of our clients in France is working on grapes that are used for wine and is very much interested to tell the farmers what is the quality and the quantity of these grapes. You know, how much Brix there is, how much moisture there is, and pH, and so on. So he provided us with these 53 spectra, and he had already measured the Brix content using a Brix meter. So Brix scale, basically, 1 Brix is 1 gram of pure sucrose sugar in 100 ml of water. So he had already measured that with the Brix meter. So we made a calibration model out of this, and then we would apply that to some samples whose Brix content was not known. But before we do that, you need to apply some basically pre-processing to the spectra, because these, as you can see, these spectra are displaced. There's a DC offset, and this DC offset is just due to scattering effects. So you need to remove this DC offset. And one way to do that would be to apply the second derivative, which we have done here. And all the peaks, the absorption peaks, would remain in the same location, but maybe the direction will be reversed, as you can see here. And this process also introduced some noise. So you need to apply a filter to smoothen the curve after you apply the second derivative. And you can do the Savitsky-Golay filter, which basically applies a polynomial to a section of the graph. So you point out how many points there are and what degree polynomial you want to fit, and you will fit the smooth line to those noisy signals over there. So after we did the pre-processing, and this is the Savitsky-Golay second derivative signal, you can see all the differences disappeared. There's no DC offset. And then we made a prediction. Basically, this is the real value, this is the predicted value, and we came up with RMSE of 0.77 Brix for this, which is not too bad. It's not the best, but because you can see that we don't have some calibration points here in this region, and our numbers are not enough for a calibration. Usually we prefer to have 100 samples at least, but you know, even though we did that, we still got a good result. R square of 0.87 and RMSE of 0.77. So this was one example. The second example was we did the protein and moisture contents of wheat kernel for one of our customers in Manitoba. So they have this device called the grain analyzer, which is a $20,000 very expensive NIRvascan instrument. So they would just put the grain in there, and the instrument will give them the protein and moisture content. This has already been calibrated against analytical methods such as HPLC, and its value is within plus minus 0.1% of the HPLC. So this is very accurate. The idea for us was to see if we could just do the same measurement by modeling and using a $2,000 NIRvascan instrument, because this would save a lot of money for people who want to do it. So we tried with different samples. It's 190. In this graph, there's 140 shown, but in fact, there were 190 samples were provided to us of different concentrations of protein and moisture. So we measured from each sample and actually we did 4 measurements. So every time we would reshuffle the grains so that new samples are measured. This is a reflective model. So we measured all these spectra, and this is also the test spectra where we want to uh, predict. So we had the protein and moisture. We also had the spectra. We made a model. So we also did the Savitsky-Golay filter, of course. So this is the calibration. This is the validation. And what we found out here is that the moisture gave a good RMSC value, 0.47, but protein did not yield the good result. RMSC of 1.73, which is not very good. So we were just wondering why this is the case, and that became clear when we looked at the scatter of the data points for the calibration. So you can see this is like the calculated response, the actual response. This is from the Minitab where you can actually see each sample. So we have a really good concentration in this region and not too many data points here. So one idea that came to mind is if we narrow down the calibration to this region where we have more points, then maybe we'll get a better result. So I applied that to only the 15 samples that lied in the region 15.8 to 18.2, for example. And that improved the prediction to RMSC of 0.52%. So that shows that you need to have equal number of samples in each region. If you apply to the full range because you don't have enough samples here and here, you won't get a good result. But if you apply it to a region where you have a good concentration of samples, then you would get a much better result, and that's what we saw. In fact, for the 190 samples, you can do the histogram, and you can see that from 12.46% to say 14.8, you have very good number of samples, more than let's say 35 in each case. Here 35, near 40, this is 45. But as you go to the size, the number of samples reduce. So if you want to make a good prediction over the full range, you also need more samples in all of these ranges as well, which we don't have at the moment. All right, so that brings us to the cloud service. So I'm going to try to demo the cloud service. So many of our customers in previous years, they were asking us, so what do you do with this NIRvascan spectra, the absorption spectra? So how can we get the sugar content, the fat content, the protein content? And our answer was no, you have to do your own chemometrics. But now we are in a position, since a few months ago, we have introduced our cloud service, and it's free. You can go ahead and try it out. This is the link for it. Basically, you could upload all your spectra on the cloud, and you can make NIR profiles. You can plot your profiles. You could make basically pre-processing, apply pre-processing to your spectra, the second derivative of Savitsky-Golay, and you can make predictions using PLS model, or you can do sorting using the PCA model, principal component analysis, or linear discriminant analysis. So this has made it very easy for our customers to basically use this cloud for free to get the ingredients that they're looking for, or to do their sorting. For example, plastic sorting, different types of plastics. So let me show you how this works. So I'm going to go on the cloud platform. Just a minute. So NIRvacloud.ai. NIRvacloud.ai. Yes. So this is the cloud platform, and I'm logged in right now, but any one of you could go there and basically just register. You need to register some information. including your email, your name, and then you can get started to go into the cloud. So the first thing to do would be to click on analysis. Once you click on the analysis, then you'll see all the different features that appear in here. So you can put your spectra there. These are all different spectra. But normally the way we do it is that we upload profiles. And this is what the first page also showed us. So upload profile. What do I mean by that? What I mean is that you make a profile, just like in that Heather Brooks page that I was showing, how she set up the spreadsheet. Same thing here. So on the first row, you have all the wavelengths from 900 all the way to 1700 over here. And then you have your protein contents here on the first column. And these are all the absorbances. So this one has, for example, 38 spectra in there. So once you do the measurements and you create this file in Excel, then you can upload all of this all at once. You don't need to do it one by one. So you can just give it a name here and then choose the file and upload it. So here, for example, I give you some example. So this is one profile, or number of spectra is also shown here. This is another. So you can see the full range. These are labels. These are the protein contents that are automatically extracted from the Excel file. You can hide the label if you want to see it more carefully. You could increase the resolution. This is low resolution. This is high resolution. And so you can display your spectra. Then the other thing that you could do is you can apply the Savitsky-Golay filter. So if you go to add, for example, then you would give it the title, the window length, the polynomial order that you want to fit, how many derivatives, and then you will choose one of these profiles here, and not from the spectrum, but from the profiles, and they say save. And that will apply the Savitsky-Golay of that number of points and that order of derivative to your profile. So you can look at some of these, for example. So these are Savitsky-Golay. So you can see this is the second derivative spectrum. In high resolution, it looks like this. So you can see that there are two, I need to explain, there are two suffixes here. One is called SG Pro. All the SG Pros are in here. But later on, when we go to PLS models, you also see there may be other profiles. Let me look at the SG filters one more time. SG Pro means it's from the profiles. So I'll explain that later. There is SG PLS. So once you make this, you can apply your Savitsky-Golay. But for making the calibration model, you don't have to start from the SG filter because it is also included in the PLS model. So you can go add a PLS model and you give it a title, a number of components you want to use, and what is the calibration profile that you want to use to apply to make the model. And then you can say apply SG filter, and that same menu appears here too. So then you would save it, and that will give you a PLS model. So I'll show you one PLS model, for example. So here I go to this PLS model. So this PLS model are already, you have the parameters, 10 components, a Savitsky-Golay of 23, and its model itself has the RMSE of 0.3. Looks like this. And then you can apply this to any one of these, any one of these other test files, which has already been applied. The Savitsky-Golay has already been applied to it. SG Pro. So if I choose, for example, this is the wheat. So for example, I choose this, and then I would say, apply the model to predict. Then it gives me the predictions. So if you scroll over this, it will tell you what the actual number is and what the predicted is. So you can also get the results, the score, the R-square of prediction, and also the true prediction. You can also export the results to an Excel file to tell you that what is the actual value and what is the predicted value. So it will give you all this information. So that's the one PLS model. SG, these are all the PLS model, right? So the other feature is for sorting. We have a customer that does the plastic sorting. So we make LDA models. So for example, here, linear discriminant analysis, we have an LDA model for classifying different types of plastics. So each one of these are separated in different piles, type 1 to type 7. So I have recorded a video on this that I'll show you later for plastic sorting. So one thing about plastic sorting is that you have to get different profiles. So let me actually show you the different profiles here. Sorry, this is not. Different profiles should be shown here for PCA, chemometrics, LDA, and no, actually it is for customers and plastic recycling. So each file of different type should be in one, you can say in one Excel sheet. So this is plastic type 1 is in this. You can see it's only type 1 and all the spectra are given here. The wavelength is on the top. And you also have type 2, type 3. So for different types of plastic, the spectra are in different files. And then you can upload all of these at once. So you go here, when you want to make your LDA model, you say add LDA model. And then you would say, for example, webinar, you give it a name, webinar March 16, a number of components 2, and then you would choose all those plastics, 5, 4, 2. No, this is from the, yes, this is, yeah, 5, 4, 2, 1, and so on. And then you would save. Okay, so this is the LDA model that uses all of those plastics. So you can see they're separated into different piles. You also have a PCA model, same method. You have to generate these Excel sheets that have different types, and then you give it a name, and all of them you can upload at the same time and then make a PCA model by using the add. Okay, so these features are very useful. The cloud service is free for people who use NIRvascan, who purchase NIRvascan. And we also give you support up to 5 hours for you to, if you have any issues, you want to learn how to use the cloud more. And I would suggest if you try it out, it's for free right now. There's also some security features. You know, you could choose your data to be secure. In that case, you will be the only one who will see it. But if you leave it open, then everyone else can see it as well. So here are some examples that I showed: the cloud service, the PLS model, the LDA model. You can create these. This was an app that was made a few years ago. It's not available, but this was just to show that you can communicate with the cloud in a two-way fashion, so that you can send information to the cloud and then receive feedback from the cloud. It's called the Deep Scan, and there's a video for it that we'll send you later. You can watch that. So the idea was, for example, you measure with the NIRvascan from a fruit, from a mango. You would choose the profile, first of all, what kind of calibration profile you want, say for fruits. Then you measure it from the fruit, and the data will be sent to the cloud. The cloud will tell you what the sweetness of fruit is. So it will compare this spectra with its calibration files, and it will tell you what the Brix content is. So here you can see fruit was measured, and it says it's 16.1 Brix, super sweet. It also classifies if it is sweet or super sweet, or not sweet. You can also measure body fat. Here is I'm measuring from my arm, from the arm where there is enough fat. You can put it there and measure it. And near IR is harmless, basically. So it will penetrate by a few millimeters, maybe up to a few centimeters even into the tissue. And it will measure the fat content, 30% there. So it's a useful app to look at. Some other examples, polyester content in fabrics. One of our customers sent us some samples and told us one of these have an extra element. So just by qualitatively observing the spectra, we saw that there's an extra peak for this sample 7, and this corresponds to an aromatic ingredient, which is toluene, and you can see that we could detect that. So even if you do a PCA model, it is guaranteed that this will separate from the other fabrics. We did some detection of fake masks. So the M3 mask has an extra peak of polypropylene, which has a CH3 bond, and that showed only for the M3 masks. So the other, or 3M masks, sorry, the others did not show that peak. So this was detection of masks. Plastic recycling is a really big basically application. We already have a customer that does this, and as I told you, the communication with the cloud is quite important. So we did also apply. We created an app that could communicate with the cloud. There's a YouTube video here that you will see. I'm measuring from different types of plastics, and the data directly is saved into the cloud. The cloud runs the LDA model and identifies the type of plastic and sends it back to me. So this was a very interesting application. So similar to DeepScan, we are able to make apps that are capable of communicating 2 ways with the customer on the spot. So if you want to do quantitative measurements, you could send the data to the cloud runs the PLS model, sends the prediction back, or quantitative. This, of course, has a lot of application in plastic recycling, which at the moment is done by manual workers. Another interesting application is some customers are asking us how to measure from, like if you have like a conveyor belt and the moving platform where there are many of the pieces are moving by. Again, this is the first time I'm showing this, how we can use that. And the idea is that you cannot use the reflective model, because the reflective model needs to touch the sample. The window of the reflective model needs to touch the sample. So if you have a moving geometry, this would not work. And if you separate the window from the moving geometry, it will reduce the signal to noise ratio and increases the noise, basically, so which is not good. However, there is a new external source. It's called the DRP1 that you can see here, and I've done a video. I have to run this video for you because this is not in the YouTube format at the moment. So I would need to play it for you. So if you if you want to run it, you'll get you would need permission to run it. So let me show you this video. It's worth watching it. The purpose of this video is to demonstrate that we can measure the absorbance of cannabis flower remotely. So here's the software that you're using, and I already named the farm that I want to measure. Just press the scan. And as soon as I press the scan, we'll see what happens to the lamp. So I press the scan, and you can see the lamp came out momentarily. And this is the reflective spectrum that we measure. For powder. So we can also look at the absorbance. We can also look at the reflectance. And here are just everything reflectance, absorbance, and reflected intensity. So this way. Okay, so that was the. Okay, so this was to show that you could do measurements remotely if you like, using the DRP1, which I said by mistake. DPR1 is DRP1 light source. Some other examples, I would look at the pointer option here. Some other examples, you can use NIRvascan to detect viruses, for example, from malaria, Zika virus in the mosquitoes. This has been used, the NIRIR, by doing the modeling. I'm going quickly through the rest of the presentation because we don't have time. The transmission model was used to measure different liquids. One has to be careful not to, for watery samples, sometimes you don't get enough signal. A signal is swamped past 1400 if you use a 1 centimeter cuvette. But if you reduce the size of the cuvette to 3 millimeter thickness, those signals will reappear. So that's the consideration. This is for soap. You can do a flu virus in nasal fluids. We have a customer who's trying to measure malaria virus in Brazil using NIRvascan. This is again measuring some, basically the spectrum of a lamp using the fiber model. You can use a reflective probe to measure with the fiber model from wheat. The flow measurement, there's a flow cell where the liquid passes through, and you could use a lamp and the fiber model to measure the sweetness content of the flow. Will be another YouTube video that will send you about the operation of the app. It could run with both the iOS and also the Android. We'll send you these two videos. Okay, and finally, in scientific literatures, we also have two papers. One paper talked about analysis of soil in Eastern Australia, where they used NIRvascan and compared it with another portable spectrometer and two other benchtop spectrometers, which are quite expensive. And NIRvascan showed a good performance. Also, the EPA evaluation portable sensor for seafood decomposition determination was also another paper where NIRvascan was used. So this was EPA paper, Environmental Protection Agency. So these are two standard papers that we show as a reference. So in conclusion, our time is up. We showed that the NIRvascan reflective model shows promising results in food industry, textile, health monitoring, plastics. Both quantitative and qualitative measurements are possible. The transmission model, we showed that it could measure liquids successfully, and the thickness of the cuvette is an important parameter that we need to take into account, because if it is too thick, sometimes you won't get a signal past 1400 nanometer. We showed that the fiber optic model could run with the DRP1 external source to measure reflectance of objects at an 8mm distance. And use of chemometrics, we showed PLS, a PCA model. We demoed the cloud service, and we also showed a custom app that can be used for plastic sorting. It has two-way communication with the cloud. So this you will see in the link that we'll send later. A similar app for quantitative prediction can also be made. So this is the end of the presentation. 2 minutes more than the allocated time. Sorry about that. So at this point, I will open the floor. If anyone has any questions, please feel free to ask. I don't know if there has been any questions at all. So does anybody have any questions? Please feel free to type your question, or if you don't want to type it, you can just unmute yourself and let me know if there are any questions. I'm going to type my email here also for you. If you think of any questions. Okay, a great present. Okay, thank you, Manuela. Thank you very much. Anyone else? Okay, if not, thank you again for your attending this this webinar. And if you have any questions, you can email me, and looking forward to hearing more from you. We'll also send you some kind of feedback form. If you have any suggestions to improve the webinar, you want something else to be explained more, please let me know. I'll be glad to hear your suggestions. I thank you everyone for attending the webinar and wish everyone a happy and safe afternoon. Thank you. Bye.